Lately, this gorgeous image of Blackpool Tower has been all the rage in flat earth circles. The original image itself that I'm showing you is something taken by Kevin Jackson, and here it is on his original Twitter feed. It has become so popular and so viral, he has decided to try and make some good out of it, and he is raising money for charity by selling copies of this print. You can go to this link, it will be down in the description, and you can go and buy yourself a copy of this Blackpool Tower wonderful image and do a little bit of good for the world. Everyone who's anyone in flat earth circles has been all abuzz with this image and whether it proves the earth is a globe or the earth is flat. I'm going to jump on the bandwagon and see if I can science Blackpool Tower. I was really inspired to do this by watching someone else's video, and I would like to direct you to that now. This is from a globe skeptic who goes by the name of Rachie, and what she decided to do was make a scale model and just see for herself what is supposed to happen, right? Not all of us love math and embrace math and decide that that is the way to analyze the world. Some of us want to see and touch for ourselves, and I think that means a lot. So let me take you through this diagram here. Here on the left is where we will put the viewer, and the green triangle represents the Blackpool Tower. The red triangle represents the mountains in the background, and we will space them out according to the real world scale. I have made this diagram. You can see these blue lines where I typed in the coordinates of those lines so that they were exactly to the scale that I wanted, so that I don't have to rely on any math at all. I just drew my diagram to scale, and then with a straight line, I can shoot a straight line from the observer point right across this vertex, which is the top of the tower, and look to see where in the distance that should cross. And we can see that that crosses at, somewhere below the tip of the distant mountain. And here's my line up to that distant mountain. And I did all this to scale and without doing any math at all, and I just draw some lines. That is what I'm supposed to see on the assumption that light travels in straight lines, right? The only assumption I have made here, I have made the assumption that the earth is flat, and I have made the assumption that these green and red lines are straight beams of light coming from, a beam of light coming from this point of the mountain comes straight towards my eye, and a beam of light from this point on the mountain comes straight here, barely grazes over the top of the tower and makes it to my eye. Now you'll note, I have meters across the bottom and centimeters up the top. This is a scale diagram, but the horizontal and the vertical scales are different. If I make this to scale on both axes, we'll just get little bumps. So I have exaggerated the vertical scale on a 50-to-1 ratio. So the verticals are all exaggerated by 50 times what they would be if I used the same scale as I did on the horizontal, right? I'm just doing that for the diagram to make it easier to see the separation between these. Because if I did not do that, then this separation would be 1/50th of what it is now, and I think you could see that that would make it a very, very tiny separation. The globers, all the globe folks, are fine with that. The way that we do the math as globers says that as long as you use consistent horizontal scale and a consistent vertical scale, those two scales can be different because all we're looking for is the gap between these lines. By changing the scale, according to our mathematics, by changing the scale, I cannot reverse the order of those two lines. All I could do is exaggerate the amount of gap. If there's a gap there, I can expand it by doing this that I've done. I cannot flip it. But after having watched a debate between Ranty and Brian's Logic on Katz's channel, it became clear to me that the flat earth debater didn't concede that. He didn't agree that that was an acceptable way to model this situation. And taking that into consideration, I will keep showing these diagrams, but what we're going to do, what Rachie did, and I'm going to repeat, is we're going to make a scale diagram where we have the correct scales on the horizontals and the verticals. So these labels are the sizes of the objects and the placements of the objects that Rachie provided for her example. And those were numbers that she coordinated with a glober to come up with those numbers. They may not be a precise representation of the Blackpool Tower photo, but those are the numbers that Rachie used. And I am more intrigued by her results than I am by the original photo, because the original photo matches the globe math very brilliantly. So that's really no surprise to us on the globe side. So that's not that interesting. What is interesting is what Rachie found. And let me show you just a still from the video. Here's that link to that video again. Go and watch the whole thing. It's very, very short. The red and yellow object is the foreground object. This represents Blackpool Tower. And this object is the background object. This represents the mountain. And what we just saw in the previous slide was that the mountain is supposed to be slightly taller than the tower. But in this image, it does not look like it. I've drawn some lines across here. Green lines to represent the foreground object, top and bottom, and red lines to represent the background object, top and bottom. And I think we can agree that the red lines appear significantly closer to each other than the green lines do, and that does not match our mathematics, which is truly intriguing. This is cause for further study, right? And so that has made me interested in it. I've decided to replicate this exact experiment on my own and see what I can see. When we get into this, the common pattern that we fall into so easily is to take sides and say, I'm a glober and therefore I reject this, right? Just the same as a flat earther might say, as a flat earther, I reject your mathematical analysis, right? I just reject it. I'm not going to look at it. I'm not going to listen. I'm not listening. I'm just going to try and make up reasons to reject it, right? And when I was combing through Rachie's comment thread on this video, I saw evidence that that I think maybe some of the globe folks are kind of falling into that trap a little bit. Some obvious complaints come to mind right away. One is, it would appear that the camera is not level with the bottom of these objects. If you know anything about this kind of analysis, we can see that according to where I've drawn my lines, where I have drawn my lines would indicate that the camera is well above the ground here. It is not in line with the bottom of this object. It is not in line with the bottom of this object. It is somewhere above, and that is what has caused this separation here between these two. If it were right in line with the bottom, we want to see this red line and this green line lining up, and they don't. So let's reject this experiment on that basis, right? Hold that though. Before we reject it, let's go ahead and talk about what that means, what impact on this experiment that has. We were expecting the bottoms to line up and there to be a gap at the top. Well, look at this. The top's kind of lined up and there's a gap at the bottom. The thing that we are really talking about is the angular size of the two objects. and the angular size barely changes at all by imperceptible amounts as we raise or lower the camera a centimeter off the floor. It's not significant to the overall finding. So let's not reject it on that basis. Let's embrace this and notice that the angular size of the far object is smaller than the angular size of the near object, regardless of the alignment with the floor. Okay? Although, let me now speculate, perhaps where I've drawn these lines is not, in fact, where the edges of the object are. I am wondering, as I look at this, if perhaps this area that I have indicated as the bottom of the yellow object could possibly be a reflection. Maybe that's reflecting off of, I believe she had it sitting on a book. Is this patch here, is that the book? I can't really make out the book, to be honest. And so pure, just blind speculation, this could be a reflection of the yellow object and not part of the yellow object at all. Hard to say. That could possibly be one explanation for why we saw what we did, but the camera not aligned with the floor is not an explanation. That's not a reason to reject this at all. So instead of just trying to find fault with everyone's experiment, let's instead try to understand what we saw. Let's discuss camera alignment and how it relates to Rachie's observation. In addition to these two rays for the tops of the objects, let's slap in rays for the bottom of the objects, right? And of course, those are parallel with the ground that they're sitting on. Rachie raised hers, by the way, she raised hers up on books to compensate for the distance from the camera lens to the floor, because you can't get the camera lens directly on the floor. And working with some globe fans, she got the advice to raise them up a little bit to account for that. And she did that. You could see she did that in the video. At any rate, let's take a look at what I am theorizing. I am suggesting maybe her camera is a little too high. So what if the camera is a little too high? Something like this, like that. Does that explain Rachie's findings? Well, let's remind ourselves what she did find. If we look at the bottom of the objects, the way I've marked it, at least, the foreground object is below the background object. And that is what we see when you raise the camera up a little bit. That is exactly the effect you get. So there you go. That's our explanation. No need to look further. But wait. Before you call it quits on this whole thing, take a look at what's happening at the top of the diagram. Because we raised the viewer height, we did not cause the mountain to poke up less, we caused the mountain to poke up more. This is much greater because we've raised the viewer height. So that absolutely does not explain why the background object appears to be lower than the foreground object. That is not our explanation here. That's not it. How about if the camera were lower? Let's lower the camera. Maybe the floor is uneven, or she mismeasured the books, or something like that, and the camera is too low. Let's examine what that does. So here we have a camera that is below the bottom of the objects. And yeah, that could possibly explain this top scenario where we have artificially caused the top of the distant object to appear to lower. So there you go. Maybe that's our explanation. Only no, look at the bottom of the objects. Again, I keep stressing that this is the way I've marked the bottom of the objects, and I'm not at all convinced that I've got these lines in the right places. I think that's really what we should be talking about, but before we can get there, we have to get through these other complaints that are flying around. I looked again at Rachie's comments today, and it's just full of these complaints about everything that's wrong with this. let's all take a slowdown and instead look at the results and what they mean. This does not explain this finding because the bottom of the images is the opposite of what you see if you do this. So this is absolutely not what happened. And it gives me an idea. My idea is that I can ensure that I've got the right level for the camera alignment if I have the bottoms of the two objects lined up in a perfectly straight line. Because if I'm too high, like so, I'm going to see the green object below the red object, right? So if I lower the camera, now I'm too low and I see the red object is below the green object. So I can do that to move up and down and slowly align it, either trying to hold it exactly in that place, or as some of you have already seen in the video, I moved it up and down so that you can pick your own spot where you want it to be. And you do your observation with my video anywhere you want it. If you want it to be level, then just pick a frame where the bottom of the object, the bottom of the foreground object and the bottom of the background object are perfectly lined up. In order to facilitate that, to ensure that my camera is in a perfectly straight line with the experiment, I have raised the entire experiment up on some cups. And we'll see that in the video here at the end, that I put everything on cups, and to make sure that I can clearly sight the bottoms of those objects, I have had the bottoms of my objects sticking out in the air so that there's no cup, no table, no floor beneath them, so that I can clearly make out the bottom of the objects, and I'll use that to align and ensure that my line of sight, my viewer height, is exactly the same as the base of the objects. I suggest everyone try that as well. Earlier, I identified a difficulty with assessing exactly where the bottoms, particularly the bottoms of Rachie's objects, were, because they're right up against the floor or the book or something that they're sitting on. And I didn't have like a really sharp line. So the ways to improve that experiment right off the bat would be a higher quality image that would allow me to see more distinctly the bottom of those objects, or creating a better contrast, which I've done by raising the objects up off of the floor so that I can clearly see the top and the bottom. What else might I suggest? A very bold highlight on the extremes of the object so that we can see absolutely that it is there, and maybe see if there's a refraction effect or something like that. Just like a black line right on the object, something like that might help. Okay, so this is what I've done, and that's why I've done it. I've already seen the complaints on my own thread of why did I do this, that this is invalidating everything, or other complaints that I haven't done anything to show that my floor is level. No, I have not. I don't know that that floor is level. It's a tile floor. I mean, it's probably as level as anyone else's floor. But what I have done is use light to level it. I have lined up the two objects, and you'll see in my video that there's a moment when the bottom of the green paper and the bottom of the red paper are aligned perfectly, and at that moment the camera is at precisely the right height. And that is why you see me moving the camera up and down in the experiment. The next criticism that I've seen on both of our videos, both Rachie's and my videos, contain this criticism of using the wrong numbers. These are Rachie's numbers. These are the numbers that Rachie got. She worked together with a glober to come up with these numbers, and we should recognize that and applaud that. That is how we move forward. Instead of trying to tear each other down, let's support each other and and so support the effort to come up with numbers that are useful for our experimentation. Now, the common complaint here is that this is not the correct numbers to represent the Blackpool Tower scenario. And that might be. I'll be honest with you, I haven't run the numbers myself. I'm using Rachie's numbers because Rachie's experiment is interesting all by itself. It doesn't have to be a perfect representation of Blackpool Tower in order to have a very interesting result that we need to talk about. That's why we're here. Let's do an observation and let's see what we see, and then let's try to learn from that observation, try to explain it. So these are the numbers Rachie used. And as you can see with these numbers, in this scale diagram, it's very clear that the red object, the background object, is supposed to be taller visually than the near object, right? Regardless of whether they're exactly the same as the mountain and the tower is not important. It is supposed to visually, according to math, according to the mathematical methods that we globers rely on, we are predicting Rachie's background object to be taller than the foreground object. And what makes Rachie's observation so interesting is that is not what we saw. Now, there's another YouTuber by the name of Roohif who is just absolutely meticulous with his math and his numbers and his locations and checking and crossing every T. He is excellent, and I'm just going to take him at his word because he has satisfied me time and time again that his numbers are going to be correct. I'm going to take Roohif as his numbers as being representative of correct, and he says these numbers would be better. Now, is this cause to invalidate Rachie's experiment? No. We can see that with Roohif's numbers, we get a slightly larger gap at the top than Rachie's numbers would have produced. So perhaps going with these numbers might accentuate the effect we were looking for. But the fact remains that with Rachie's observation, we got the opposite result. We did not get the background object larger, and we were expecting to. Once again, let me stress, it is not whether Blackpool Tower was correctly simulated that is interesting to me. What is interesting to me is whether the math of perspective was demonstrated with a real-world observation or not. If the flat Earth folks can repeatedly, clearly demonstrate that our math of perspective does not match observed reality, that is a finding of great significance. And so that's something we should take seriously, right? That is what we're investigating, and whether the numbers are exactly matching any particular scenario is really beside the point. I will also point out that there are several different mountains in the background, and I'm not sure which one each of you is choosing. You might well be choosing different mountains, right? So keep that in mind before you start accusing each other of trying to cheat. No one's trying to cheat, at least Rachie is not. She, in good faith, used numbers that were provided to her by someone from, the opposing team, right? That's working together to get things done. And Roohif's numbers are here, and I'm sure they represent something legit. When I did the experiment, I was trying to use Rachie's numbers, but I made a mistake. And my tower matches Rachie's exactly, but my background object is slightly too large. And so my example lands right in between Rachie's and Roohif's numbers. So I'm somewhere in between in that spectrum. And because of that, I consider it's fine, right? Once again, the interesting thing is, can I reproduce this result where the mathematics of perspective does not match the visual observed result. That's what I'm trying to get to. Speaking of mathematics, what I'm interested in specifically is the angular size of these different objects. That's how perspective really works, is based off of angular size. The irony, of course, that I've recently heard some flat earth folks complaining about how we globers never refer to angular size. And that struck me as quite odd, extremely ironic to hear, because I can't speak for everyone, but I will tell you that I have spoken of angular size at some length and tried to explain how that works. I've definitely heard Roohif go on about angular size and several other globers as well. I think it's kind of our go-to. And the usual approach for that is to use some trigonometry. And then that's where we sort of lose our connection with the flat earth audience. I was talking to a friend of mine who is a flat earther, and he reminded me that most people, just most general people out there, do not remember their trigonometry, if indeed they even took trigonometry in the first place. If we just look at all the people of the world and just grab someone at random and ask them what an arctangent is, I don't think most people are practiced with that, and I don't think that is a good starting point for this conversation when there's already a mistrust and perhaps an animosity. We don't need to rev that up by fighting over whether trigonometry is good or not. We don't need trigonometry. I'm going to show you how we can do this whole analysis with just ratios. This line, this green line, is a perfectly straight line, and I made it as a straight line here in PowerPoint. And it's the line going from the observer right across the top of the tower and extended forward. We see that it intersects the mountain below the top. I have made the assumption that light is traveling in straight lines. That assumption alone allowed me to construct that diagram. We'll hear complaints that perspective is not taken into account. That is perspective. There's not a diagram of how things look. This is a diagram of how things are. The near object is smaller than the far object. The viewer is over here, and the effect of perspective is caused by the assumption that your brain makes. Your brain is hardwired to assume that light travels in straight lines. And from that, we get the perception of perspective. And check out my video on that. So this is a diagram that shows not how objects appear to be, but how objects actually are. The object in the foreground is close but small. The object in the far field here is large but far away. And they appear to be similar in size, and that in fact is perspective. These lines are showing the perspective. Let me show you what it would look like visually if we were to take a picture from this location. It would appear as though the green triangle were this large in comparison to the red triangle. That is perspective. That is exactly the effect of perspective. And yes, this diagram does show it. That is what the green line here is representing. That is where we can use ratios instead of trigonometry to represent this whole scenario. The ratio of height to distance is the slope of this green line. And we can see that the red line is steeper. It has a larger ratio. It has more up as opposed to across than this one does. Now, here's the math we're going to do here. Not a lot. Let's just take these as a ratio. We'll take the height as a ratio compared to the distance, right? So we have 1 centimeter as a ratio here over 1 meter. This is how tall compared to how far away. All right, that's just what that is. How tall is a ratio of how far away. And I will convert that from centimeters to meters, and that's what we get. And the m's will drop out and divided by 1, that's nothing. So we have a ratio for the green foreground object of 0.01. That's the ratio of how tall it is compared to how far away it is. So 1/100th. Let's do the same thing for the red object. We get 0.1125, slightly larger number than this. These numbers represent the slope of these two lines. And I don't need trigonometry. I don't need anything other than just, I'm going to take ratios. So the red object is visually larger. It has a larger ratio of height to distance than the green object has. How much larger? Let's express that as a percentage. So I'm just going to convert from raw numbers into a percentage. How much larger is it? It is, well, how much larger? We just subtract them, right? And we'll get 0.00125. But then if we want to express that as a percentage, we'll divide by the original object's ratio. So how much bigger is it? It is 0.125 bigger. It is 12.5% larger. 12.5% happens to be 1/8. What are we saying with that? What we're saying is, if we were to look from here, the visual size of this object would be, the green object's visual size, it would appear to intersect the red object at the 4 centimeter point, leaving 0.5 centimeter at the top that we have not, that it doesn't block. So we were expecting to see 0.5 centimeter of our 4.5 centimeter red object poking up over the top of the foreground object. Reminding you again, what did we actually see? Not that at all. We saw that the distant object is measurably smaller than the near ground object. Inspired by this, I wanted to see whether I could reproduce the same effect at home. So I went and got some construction paper and I folded it, and I carefully folded a green piece of construction paper at exactly 1 centimeter. This is 10 millimeters right here, and did a good job with that. And then I took and made a red piece of construction paper, and I botched it a little bit. As you can see right there, I missed the fold. I'm at 46 millimeters or 4.6 centimeters. And I was thinking about redoing it, but I was like, you know what? That's close enough, because it's between Rachie's numbers and Roohif's numbers. So I'm like right in between there. And we've already shown that that doesn't make that much of a difference in the overall scheme of things. I'm interested to see if I can replicate that effect where the object doesn't match the mathematics, right? So I'm going to go with 4.6 centimeters on my back object. Now that means my ratio is a little bit different. Got the same ratio for the foreground object, but the background object, which I have still placed at 4 meters, instead of 12.5%, I should get a difference of 15%. So I'm looking for the red object to be 15% larger visually than the green object at these distances. Let me start off by just showing you the still of my final result, and it worked. The green is the foreground object that represents a Blackpool Tower that is 1 centimeter tall, 1 meter away. The red is the background object that represents the mountain in the distance that is 4.6 centimeters tall at 4 meters away. I'll share my whole video on this shortly, but let's just start straight with the results. This is a pretty close match to what the mathematics suggested. Now you're going to notice one difference right off the bat between the way Rachie did it and the way that I did it. And that is, I have mounted these things on plastic cups. I have a handful of these identical plastic cups, and so I set them on the floor. And I have used that to raise the construction paper up off of the floor. Now the main reason for that is so that I can align the camera with the base of the mountain, right? I want my observer to be down on the ground level where the base of the mountain should be. But the camera, of course, is, a good centimeter away from the edge of the phone. I'm taking these pictures with my phone. It's a Samsung, it's Galaxy Note 20 Ultra. So it has cameras, has multiple cameras, and they're at least a centimeter away from the edge of the phone. So I cannot get the lens on the ground. So raising the whole thing up just a little bit off the ground, I'm able to line things up perfectly. This also eliminates the problem of people complaining that it's not lined up. Like, oh, it's not on the ground. I can tell it's not on the ground. Well, I can move it up and down. Okay, so as I take the video, I do move the phone upwards and downwards. So if you don't like where I took this shot, you think I'm a little too high or I'm a little too low, just go forward a frame or two until you like it, right? It's that way you have room to wiggle and get beneath. You can even explore what happens if I go below ground level. The other main reason is that one of the complaints or one of the criticisms you're going to get is, how do we know that floor is level, right? Sure, these cups are the same height, but they're on ground that might not be level. Haha, those objects might not be at the same height. And my answer is, I will line up the camera so that they're in a straight line, whether that line is 100% perfectly horizontal or maybe it's tilted a little bit. It doesn't matter. We're comparing the angular size of these objects at these distances, right? And so just get it up off the ground. No one complains about the effect of the ground. What I wanted to do next was to ask the question, how close to the mathematical prediction am I with this observation? What I found when I tried to measure the pixel size of my images was that it was very difficult to focus on both the foreground and the background object in the same photo. So here I have an example where I have focused on the foreground object, and I used this frame to measure the height of the foreground object. And that came in as 166.5 pixels. Now, if you're curious about where that 0.5 pixels comes from, it's because you can see in this photo, I was not holding the camera perfectly level. And again, that doesn't mess up the results. That just means I need to measure the height of my mountain at a slight angle. And GIMP told me that that came in as 166.5 pixels. All right, but look at the background object. Look how blurry that is. If I were to try to measure the height of that, I don't know. I mean, I don't know where is the top of this object, where is the bottom of this object. I can't tell. So what I'll do is, I'm holding the camera still, I change the focus onto the background object so I get a nice sharp background object, and the foreground is all blurry now. So then I measure it again and I get 193.7 pixels. All right, so we crunched the math. What did we find? We got the background object is 16.3% larger than the foreground object. That's the measured result. And so that is what I got. I was expecting to see a 15% larger background object, and I measured a 16.3%. So I'm off by 1.3%. That's pretty good considering, I'm measuring my distances with a tape measure and my heights with a ruler, and I'm just using a cell phone to take pictures. That's That's pretty good. So my results seem to confirm the mathematics of perspective. On the other hand, let's compare with Rachie's results. For her results, we were expecting from the math a 12.5% larger background object. But according to my measurements, which are pretty suspicious, it was a 21.6% smaller object, giving us an overall error of 34%. We're off from the math by 30% here. And that is the interesting finding in all of this, is that something about the way Rachie did this experiment has produced something that does not match the mathematical prediction. Something in the difference between the way we've conducted these is where the interesting thing is. Talking about whether this is a perfect representation of the Blackpool Tower photo is, for me, a huge distraction away from the interesting thing, which is there a systematic way to produce this result that seems to show that the math of perspective doesn't match visual reality? And if we can find what that is, then can we apply that to the Blackpool photo, right? That's where we should all be striving to do. If you are a flat earther out there and you want to shout at me because you don't like the fact that I raised this up on cups, don't shout at me. Use that as a data point, right? Create a hypothesis. I hypothesize that the reason that the math didn't work in Rachie's is because she did it near the ground. Let's test that hypothesis. We'll do it on the ground. We'll do it up in the air. Is that the reason? All right, and then we'll come back and we'll study it more. Could there be other reasons? Another thing I want to study. I want to study focus. Can we get a sharper focus here? A sharper focus on the foreground object in particular, or a sharper edge. I'm not sure that I marked the bottom of this edge correctly. The bottom of that object was supposed to be lined up, and that's something else that did not occur correctly. So can we see this bottom edge better somehow? And what can we learn from that? Let's do that experiment. So let's do those experiments. And everybody, get out there. I know a bunch of you out there have P900s. You have better cameras than Rachie does. You have better cameras than I do. So get out there. Grab your measuring tape. Do this. Take these pictures and share with us. Share what you find. And let's create some hypotheses about what this difference is about. And let's do some experiments to find out. Let's science it, right? Instead of shouting at each other, let's do a science. All right, so looking forward to seeing everybody's stuff. I'll now tack on to the end of here my full video showing, basically what I already showed, the experiment as I did it. So let me start off by measuring the green paper that represents Blackpool Tower. That is 1 centimeter exactly. And now for the background, I have a red piece of paper, and I made it just a hair too big. That is 4.6 centimeters. So we are going to be expecting a slightly larger background than we saw with Rachie's demo. So here I am measuring the distance to the object. Like Rachie did, I have only in inches on my tape measure. So that is 39 3/8 of an inch from the viewer's position to where I've mounted my Blackpool Tower simulation, which is the green paper. And then we'll take it to the distance. The distant mountain will be at 4 meters, which comes out as 157 1/2 inches. So I'm carefully placing the mountain at the correct distance. All right, now let's head back to the start and see what we see. The starting point is right at 0 inches. So I move forward into position
And right away, even at standard focus, it appears as though the mountain in the distance is larger than the near ground object. But we'll zoom in. As I continue to zoom in, you're going to see a pop. That is not a camera cut. That will be the camera switch right there. It's a multi-lens camera on a cell phone. And so as it gets to that point, it chose a different lens. That's what just happened there. Okay, I move it up and down so that you can pick your height anywhere you want. Just grab a frame there. And it's clearly showing that the background object is substantially larger than the foreground object. But I do want to investigate what happens as I change focus, because the foreground object right now is out of focus and a little blurry. So I'm going to focus on the foreground object, nice and sharp. But look at how blurry that background object is there. Which is bigger? Hard to say. Oh, but now as the focus changes, we're back to the background object being substantially larger. Once more, let me show the dramatic impact of the focus change. Yeah, that's going to be one of my top hypotheses to test. Could this focus change be the reason that the measurements came out so different?